Problem 21. Steph scored 15 baskets out of 20 attempts in the first half of a game, and 10 baskets out of 10 attempts in the second half. Candace took 12 attempts in the first half and 18 attempts in the second half. In each half, Steph scored a higher percentage of baskets than Candace. Surprisingly, they ended with the same overall percentage of baskets scored. How many baskets did Candace score in the second half than in the first? First, we can label Candace's first half as A over 12 and second half percentage as B over 12. So since we know that Steph ended with a higher percentage of baskets than Candace in each half, we know that 15 over 20 is greater than A over 12, and 10 over 10 is greater than B over 18. We can then simplify these inequalities by multiplying by 12 on both sides over here, and we get 9 is greater than A, and then by multiplying by 18 on both sides over here, so then we get 18 is greater than B. Then using the last piece of information we have, they ended up with the same overall percentage. So if we make a total column over here, we can find the overall percentage by adding the total correct in both halves, 25 over the total attempts, which is 30. And then over here for Candace, you'll have A plus B over 12 plus 18, which is also 30. So setting these equal, we have 25 over 30 equals A plus B over 30. We can multiply by 30, and then on both sides, and we get 25 equals A plus B. However, there's only one solution satisfying both of these inequalities and this equation. If we set A to its maximum value of 8, and B to its maximum value of 17, we see that 8 plus 17 is 25. So this is the only solution that works. So we can see right here the question asks for how many more baskets Candace scored in the second half than in the first. So if she scored 17 in the second half, and then 8 in the first half, that is a difference of 9, which is answer choice C. Problem 22. A bus takes 2 minutes to drive from one stop to the next, and waits 1 minute at each stop to let passengers board. Zia takes 5 minutes to walk from one bus stop to the next. As Zia reaches a bus stop, if the bus is at the previous stop or has already left the previous stop, then she will wait for the bus. Otherwise, she will start walking toward the next stop. Suppose the bus and Zia start at the same time toward the library, with the bus 3 stops behind. After how many minutes will Zia board the bus? We can solve this problem by tracking the location of the bus and Zia every 5 minutes. After 5 minutes, Zia moves 1 stop forward, and the bus moves 1 stop forward here for 2 minutes, 1 minute for passengers to board, and then 2 more minutes to go to the next stop. Since the bus is not 1 stop behind Zia, she keeps moving. So after 10 minutes, Zia moves 1 more stop forward. The bus waits 1 minute for the passengers to board since it wasn't able to in the last 5 minutes, moves forward to the next stop for an extra 2 minutes. That's a total of 3 minutes. Then it waits for passengers to board for a total of 4 minutes, and then moves halfway forward for a total of 5 minutes. Since the bus is still not 1 stop behind Zia, she keeps moving. She moves to the next stop here after 15 minutes, a total of 15 minutes. The bus moves all the way to the next stop, so that's 1 minute because it was halfway. Then it stops to wait for passengers for 1 minute, so that's a total of 2 minutes. Moves to the next stop for an extra 2 minutes, and then waits for passengers to board, which completes that 15 minutes. Now the bus is 1 stop behind Zia, so she'll wait for it to catch up. It'll take 2 minutes to catch up to her, and then she can board it. So that means that the answer is 15 plus 2, which is 17. Answer choice A. In problem 23, we are trying to find out how many configurations of this tic-tac-toe-like grid there are where we have 3 triangles in a line and 3 circles in a line. First, we can figure out where the triangles could go. So obviously, we couldn't have this diagonal pattern because then there would be no way for 3 circles to be in a line. So that means we can have the triangles going either vertically or horizontally. So we can multiply by 2 because it doesn't matter, whatever we do, we could just rotate at the end. And then we can see here that the circles can fit nicely either here or here, but we have to be careful and create two cases in order to avoid overcounting. Because if we have two rows of circles here, for example, you might count the triangles and the circles as one case here, then these triangles and circles as another case here, when really they're all one pattern. So if there's a duplicate row, there are two ways to choose which shape you're going to have a duplicate of. You could have the two rows of circles as shown here, or you could have two rows of triangles. So we multiply by 2 again. And then there are three ways to rearrange these rows. So for example, there are three ways to choose where the circles could go. So that's multiply by 3 again. So this case gets you a total of 12. Then right here, second case, oh, I accidentally switched these up. Is one of each. So again, we could have either horizontal or vertical, but we'll be assuming horizontal here. And you can have one of each row, one row of triangles, one row of circles. So there are three ways to choose where the triangles could go, and if we put them in the top row, right here, then two remaining ways to choose where the circles could go. As you can see, we chose the bottom row right here. And then this final row, we want to make sure that we don't count cases we've already counted in this pattern. So notice that each square could be filled with a triangle or a circle. And for example, you could have triangle, circle, triangle, or triangle, triangle, circle. But what you don't want to do is count triangle, 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 because that would be identical to the case right here. So there are two ways to choose what will be in each box. But we want to subtract triangle, 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 and circle, 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 because that will be overcounting things we already counted in case 1. So that means we'll have 2 times 3 is 6, times 2 is 12, and then this is 8 minus 2 is 6, so 12 times 6, 72 for this case. So 12 from case 1, 72 from case 2, that adds up to 84, which is answer choice D. Problem 24. The figure below shows a polygon ABCDEFGH consisting of rectangles and right triangles. When cut out and folded on the dotted lines, the polygon forms a triangular prism. Suppose that AH equals EF equals 8 and GH equals 14. What is the volume of the prism? First, we can fill out the values we already know. AH is 8, EF is 8, and GH is 14. Then we can think about how the net folds up. So we know that these triangular sides are going to fold inwards, and this might be the back of the figure, and this will fold up to be the bottom, almost like this. So we know that this side, GF, is going to adjoin EF right here. So that means that they're both equal to 8. And we know it's a rectangle, so this side is also 8. And then similarly, AB is going to adjoin BC up here. So we know that this is also 8. And then a rectangle, this side's also 8. Therefore, JG is 6. And this is 8. And now we can fill out these values on our 3D model. And we know that the volume of this triangular prism is the base of one face times the height. So in this case, the base is a triangle, so it's 1/2 6 times 8. And then The height in this case of the prism is 8. So this is equal to 24 times 8, which is equal to 192, which is answer choice C. Problem 25. A cricket randomly hops between 4 leaves, on each turn hopping to one of the other 3 leaves with equal probability. After 4 hops, what is the probability that the cricket has returned to the leaf where it started? We can solve this problem using casework. We can call the leaf where we start A and the other 3 indistinguishable leaves B. So we know we have 4 hops. You start with A and end with A, and then from A you have to go to B, and then in order to get back to A, you have to go to B. So there are 2 values that you can fill this intermediate spot with, either A or B. So by finding the probability of going from A to B, B to A, and B to B, we can fill this out very quickly. So from A, there are only 3 ways to move, and all of them go to B, so there's a probability of 1. Then if you're on leaf B, there are 3 ways to move. One of them is A, which leads you to a 1/3 probability here, and 2 ways to go to B, so a 2/3 probability of going from B to B. So filling this out, we know there's 1 probability of starting with A, probability of 1 from going A to B, then B to A has a 1/3 probability, A to B has a 1 probability, and B to A has a 1/3 probability. So this case has a probability of 1/9. Then the second case down here, we start with A, probability of 1 from going from A to B to B has a 2/3 probability, B to B has a 2/3 probability, B to A has a 1/3 probability, so this case has probability of 4/27, making a common denominator up here, 3/27. We can add these 2 cases together and get the final answer of 7/27, which is E.